Hello. In this video, I'll explain the procedure of Gauss-Jordan method to solve a system of linear equations and how to develop its algorithm and Python code. A system of n number of linear equations can be expressed by using a matrix vector equation of three components. On the left side, the coefficients matrix, which is called A matrix, multiplied by the vector of unknown variables x, and on the right side, the vector of constant terms, or B vector. The solution of the system is the values of the elements of x vector. The goal of Gauss-Jordan method is to transform the system so that the A matrix becomes the identity matrix of the same size where, as you see here, all elements on the main diagonal are ones while all other elements are zeros. This procedure will consequently transform the B vector to the solution vector at the end of n number of transformations. Gauss-Jordan method is one of the elimination methods since it depends on the matrix reduction by using row subtractions at each transformation. I'll use this symbolic system of four equations to explain the method. The superscripts in the parentheses indicate to the number of the applied transformations at each element. So the original system here has 0 transformations. Since the elements of the identity matrix are either ones or zeros, we can divide each transformation to two main steps. First, making the pivot elements on the main diagonal equal to 1, and second, to make other elements in the pivot columns zeros. We start with the first column. So the first step is to make the pivot element A11 equal 1. This is made by dividing the entire row 1, including the B element, by the pivot element A11. As a result, this gives the first transformation of row 1. This can be written in form of equations as following. So the first transformation of the elements from A11 to A14 are equal to the old values of these elements divided by A11. This, of course, will lead to the value A11 as the first transformation. And also, we do the same operation to get the first transformation of the B1 element. The second step is to reduce all elements under the pivot to 0. We start with the element A21. The pivot element, which is now equal to 1, is used by multiplying the entire row by the value of the element A21, then subtracted from the row 2. So this operation can be written at each element in row 2 as that A21, which is just under the pivot element, will be equal to the old value of that element minus the factor, which is the same element multiplied by A11, while the other elements like A22 up to B2 will have different values according to the operations they subjected to. Now, the same operation can be repeated exactly to row 3 and the row 4. At the end of these operations, we will get the first transformation of the whole system. And as you see, the first column now is transformed as the first column of the identity matrix. The second transformation will show us how to transform a row above the pivot row in order to zero the elements above the main diagonal. The steps are exactly the same as the first transformation. First, we should divide the pivot row by the pivot element A22. Now, to get the second transformation of the row 2, this operation can be written as following. So the elements from 22 to 24 by A22, and this will yield that the pivot element will be equal to 1, and also we apply all this operation up to the B2 element in the B vector. Now, to transform row 1, we multiply the entire pivot row by the value of the element A12, then we subtract it from the row 1. This can be written in the following equations. So A12, the new value in the transformation 2, will be equal to the old value minus A12, which is the common factor which is to be multiplied in the whole row 1, multiplied by the pivot element, which is equal to 1. So it will give us 0 value for A12, while the other elements will get different values according to the corresponding elements in the pivot row. Now, in the same way, we apply the same procedure to rows 3 and 4 in order to get the second transformation of the whole system. And in this way, we continue until we get the transformation of the whole system. Now, let's write the equations of each transformation as general formulas by using symbolic subscripts. So the equations of step 1, where we divide the entire pivot row by the pivot element, are written as following. So the new value for the elements in the pivot row, where k refers to the pivot row and j to the columns, so we divide all elements of coefficients matrix by akk, which is the pivot element. Also, we do the same operation to the corresponding b element in the constant terms vector. So k refers to the rows and columns of the pivot elements, which are going to be transformed to ones, and which it should be cover the whole coefficient matrix from first to the last row. J is the operator or the counter which goes through the columns in order to perform the division operation within the coefficients matrix. The step of subtractions or eliminations uses the new values of the pivot row. So the transformation of any element aij will equal the old value of aij minus the factor, which is aik, which refers to the corresponding element on the pivot column for that row, multiplied by the new value of akj on the pivot row. Also, we apply the same operation to the corresponding b vector element, where k is the index of the pivot rows and columns, I is the index of the rows during the elimination process above and below the pivot row, and j is the indicator or the index of the columns inside the coefficients matrix. We should take into consideration that during the loop of I should never equal to k, because the pivot row, which is referred here by the index k, is already transformed in the step 1. Now, we have two important notes in this point. If an element in the pivot column is 0, so the elimination of its entire row should be skipped. Because of the division by the pivot element at each transformation, the pivot element should never be equal to 0. So the partial pivoting process should be applied at each time. Up to this point in this lecture, I used the common index or subscript system of matrix and vector elements in most textbooks of numerical analysis and mathematics in general, where the index of the first element is 1 and the last element is n. But during coding, the array index system of the computer language should be taken into consideration. In Python, the first element of an array has index 0. And for n number of elements, the last element has the index n-1. For that reason, the subscripts of the system should be like this. From now to the end of this tutorial, I will use the Python index system. So please pay close attention to this point if you are going to code with another language. The algorithm of Gauss-Jordan method includes the two steps as following. The k loop goes through the pivots row. According to Python index system, it goes from 0 to the last row n-1. In the last video, I explained how to perform partial pivoting technique to Gauss elimination method. The same script of the partial pivoting can be applied here without any changes. Before the division of the pivot row, the pivot element AKK should be saved in a variable. We call it pivot. The reason is that AKK will be transformed to 1 before the division of other elements in the row. Consequently, if they were divided by AKK, they would be divided by its new value, which would give us wrong results. The J loop goes through the columns of the pivot row from k to the last column n-1 to divide it by the pivot element. Similarly, the B vector element in the pivot row. The I loop applies elimination to the rows above and below the pivot row, so it covers all the rows of the system except the row which it's already transformed and rows which are already have 0 elements in the pivot column k. Exactly as we have done with the pivot element value, we save the value of the pivot column element of the row I in a separate variable for the same reason. Let's call it factor. The J loop includes the subtraction step of the element of each row on the corresponding column. Finally, we apply the same process for the element of the B vector. The calculation of the B vector element can be put just after computing the factor above, because it doesn't depend on any values from the J loop. I've put it here just to keep it in the sequence shown in the previous slides. Before coding, let's solve this example and find the solution in order to verify our code. To simplify the calculations, we put the system in a simpler form. Our goal is to transform the main diagonal to 1s and the elements above and below the main diagonal to 0s. The pivot element in the first row, the first column, is 0. So from the very beginning, we should apply the partial pivoting by exchanging the two first rows. So in this way, we can start with non-zero pivot element. You notice here we have another 0 in the main diagonal and the row number 2 and column number 2. So this 0 can be changed during the elimination process for the other rows. So now we start here the solution first by starting by the first column, and we divide the first row by the value of the pivot element. So we get this transformation of the first row. Now we apply the elimination for the rows 2 and 3. You notice here I have skipped the row number 1 because we have already a 0 at the required position. So after elimination, we get this first transformation of the system. Now we will start again with the second column. So we repeat the same process by dividing the second row from the pivot element up to the B column by the value of the pivot element 2. So we get this transformation. Then we perform the elimination 0, 2, and 3. Of course, you notice here that I skipped the row number 1 because it has already been transformed. Now we get the second transformation. Now we start with the column number 2, divide the row number 2 here by the element of the pivot position, and we get this transformation of the row number 2. Now we proceed with the elimination steps of rows 0 and 3. Again, we notice that we have skipped the transformation of row number 1 because we already have a 0 element in the required position. This elimination will give us the transformation number 3 of the system. Now we go to transform the last column. So we divide the row number 3, the last row, by the pivot element, and we get this transformation of the row number 3. Now we perform the elimination to the rows 0, 1, and 2 in order to get this final transformation. As you see here, we have obtained identity matrix at the position of the coefficients matrix. So accordingly, the solution will be the values of the B column or the B vector. So at the end, the solution of the system will be these values. Now, we start the coding of the method by importing the NumPy library. Then, instead of writing the code in an open script, we can use a function. So we'll define the Gauss-Jordan function. I'll use a shortened version of the name, like this. You can select any name. So, and it will take 2 arguments, A and B, the matrix of coefficients and the vector of constant terms. We define the A and B as arrays. The reason of this step is to ensure that the arrays A and B are NumPy arrays during the code or during the run-in, because we can send them to the function as Python lists or NumPy arrays. So in both cases, we should secure that the A and B arrays are NumPy arrays in order to perform the operations we need to do. Now we define the length or the size of the system, so we can use length B. So NumPy function shape can be used also as well. Okay, now we start the main loop of the method. So we begin with for k . So in this way, k will take all elements from 0 to n minus 1. Remember, the range function in the for statement goes to the element just one before the mentioned here. So it will go to n minus 1. Now we start the script of the partial pivoting. Yeah. Now we start the algorithm of the Gauss-Jordan method. So we start with the step 1, the division of the pivot row. So we will define the value of pivot, which is equal a kk. So this is the division part. Now we start the elimination part. Or the elimination step in the Gauss-Jordan method. So we start with the loop of I. Now, in this way, we ended both loops of the step 1 of division of the pivot row and the second step of elimination loop. Now we can end the function by return statement. So we write return and 2 values, b, the solution, and let's also return a to check the elimination of Gauss-Jordan if it goes correctly or not. So in this way, we ended the function. Let's now define the A matrix and B vector. And we can simply now define them as 2 Python lists. Now let's call the function and get the solution. So let's say x and a, the values of the solution vector and the transformed A matrix are equal to Gauss-Jordan A and B. Now let's print the results. So let's say print now let's run the code and check the results. So as you see here, we obtained the solution, the exact solution as we solved the problem manually, and the transformed coefficients matrix shows that the transformation is successful to the identity matrix. If you like this tutorial, please hit the like button and don't forget to subscribe and turn on the bell to be notified for the coming videos. Thank you.